You can also use it for if your one side is hot, one side is cold. You can also then collect power off of it. So looking into potentially if I can figure out how the damn things work, how you can make it more efficient. Because they currently only operate about 5% efficiency. I'm not sure if that's the thermodynamics or what.
Mm-hmm.
Okay, I'm back, and I hope it will be a little better because I stopped several services. Do you hear me and do you see slides?
Yes, it looks like your video is muted, but I can hear you.
Yeah, I removed disabled video because it was taking too much, and there will be options for us to see faces maybe later. I just want to. So the main achievement that we've made through last month that we separated electronic and nuclear degrees of freedom, and we already got an idea how the optimization of geometry works and what one should and could do with nuclear degrees of freedom. Neglect quantum properties and either optimize geometry or run molecular dynamics. So right now we are looking on the equation on the left top for electronic part. So we need to find the at least ground state energy of a multi-electron system that we can later forward towards optimization of geometry as a planned minimum. In fact, it is much more interesting, and one can find not only ground but some excited states, but the primary goal is just ground state energy of system of many electrons that feel, experience attraction by a set of nuclei to several nuclei that determine the molecule and repel to each other. Okay, so this is the algorithm, and I will send to everyone little homework to practice this algorithm once again. So when we were looking for molecular Hamiltonian, we were having 5 terms, and 2 of them were dealing directly with nuclei. Right now we can cross them out, cross out kinetic energy of ions and potential energy of nuclear repulsion, and keep only 3 that deal directly with electrons. Their kinetic energy, the attraction between electrons and nuclei, and repulsion of electrons. So this is the equation that we will be solving for this chapter and next chapter, so for about slightly less than 2 months. And there is a substantial challenge. Right now, if you see, there is a phi sub a on the left and right part of the stationary Schrödinger equation, right? And it does depend on all electronic coordinates, which is a lot, and we need to fear off the number of electronic degrees of freedom first, and second, recognize the symmetry of the electronic wave function. And the third one, we need to pose a goal. The goal will be very clear, reasonable, and evident. We will see in a couple of minutes that amount of degrees of freedom is too high, and although we did a lot of simplifications, if we will follow literal processing of each electronic degree of freedom, it will be still too expensive for most of computational power. So we will need to simplify to simplify this Schrödinger equation from multi-electron form to something more tractable, at least for initial consideration. So, same game as we played before. Suppose that for each Cartesian coordinate of each electron, so for one electron it's 3 Cartesian coordinates, we split space onto 10 grid points, which is very rough. It's just easier to do estimates because we're splitting on grid points because we are looking for numerical solutions. And then the number of data points to treat numerically the electronic wave function will be 10 to the power of number of degrees of freedom, right? So if we have this phi sub a as function of position of electron 1, position of electron 2, and as many electrons as we have, and then for each electron we do have 3 Cartesian projections. So for hydrogen atom, described purely numerically with very rough sparse distribution of grid points, it will be 10 to the power 3 grid points, which is okay. For hydrogen molecule with 2 electrons, it will be 1,000,000 of grid points, right? Because each of the degree of freedom is independent. So, and we need to set up a table with 1,000,000 points. If we look for atomic carbon, which has 1s2, 2s2, 2p2, total 6 electrons. So 6 times 6 electrons times 3 Cartesian projections will be 18. So 10 to the power 18. And it is only 1 atom of carbon. You already see that 10 to the power 18 is about at the edge of modern computational facilities to process. If you select numbers higher than that, it will be untractable. And if you take very humble molecule with 2 carbons and 2 hydrogens, acetylene that is used for, well, right now I'm not sure if it is used, but like 100 or 50 years ago yet, it was used for welding. Like there is electrical welding and torch welding, like gas welding. But so 14 electrons, 6 times 2 from each carbon and 2 from hydrogens, 10 to the power 42. I think this example may sound convincing that literal processing of each electronic degree of freedom is too much for us. And some tricks will be needed towards finding electronic structure and finding total energy that we already know how to utilize. Like at least if you want to optimize geometry, you need electronic energy. Okay, so it will be not a big intrigue and wonder that our goal is to factorize solution, practice separation of variables, if it is possible. It is clear that with this Hamiltonian, it is not possible. It will be not legitimate to factorize, but we will try any opportunity to represent this function of many variables as factors and find each of the wave functions in the product independently, because even if it is not quite right, it is the only thing that we can do. If we want to describe molecules larger than diatomics or than acetylene, it's just we do not have choice. And here is the question, like we know that representing wave function as a product is not ideal because they interact. But if we accept it as a poor man solution, will it be how good and how bad, and other simple corrections that will make these products a little bit better. Like, should it be simple product, or maybe there is some correction that will make things a little better. So there is a key factor that due to electrons interact, electrons have spin 1/2, and if one swaps two electrons in the system, the wave function is expected to change sign. And there is a way to construct product of wave functions in such way that this property of changing sign of wave function if swapping two electrons will be mitigated. So there is a way to take care of it. And as soon as we offer such functional form of the in which we will seek the solution, then it will be sufficient for today's meeting. So if you were exposed to some level of physical chemistry or just physics, you may have heard of Pauli principle. Yes? David should shake head and tell yes. Okay, good. And Slater determinant. Yes or not quite?
That one sounds weird. I'm not positive.
Okay, so luckily or unlikely, this is not a theoretical course. We need only practical skills. So we get through this concepts only at level of acquaintance and giving them names. But the concept of oh, can you tell to Kurt and me what is Pauli exclusion principle? Just what do you think? What is your opinion or memories?
It's the idea that your electrons have to be in opposite spins.
Once again, I'll put sound a little stronger on my side. So
yeah, there's better ways to explain it. That's the way it's stuck in my head.
There are no in a given molecule, in a given system, each electron exists with a unique set of quantum numbers.
Yeah.
So the electrons do not repeat their features. So if we place an electron to the like an orbital in an atom, and then we place there a second electron with the same energy, same angular momentum, then this electron should have at least different spin. Sounds familiar?
Yeah.
Okay. So the electrons do not just there are laws of nature that forbid electrons to be in the same quantum state, and it is not so much like legal law. It is just if you will try to place two electrons to the same spot of space, or to with the same angular momentum, or with the same spin, there will be energy penalty that will be infinitely high. They will resist as much as they can against attempt to place them in the same state. Make sense? A little.
A little bit, yeah.
Okay. Well, you are lucky probably because of not enough people today. We will repeat this material again on Tuesday, so we will go over once again. So the challenge that we want to address is to design a way to factorize many electron wave functions in form of one electron wave functions in a such way that it will take into account this crazy features about symmetry, about Pauli exclusion, that we are going to practice standard separation of variables that people do in partial differential equations. But in this specific case, one needs to add together another concept, to add there a concept of the Pauli exclusion and antisymmetry of wave function that happens if one swaps two electrons. And this antisymmetry of wave function is another reflection of Pauli exclusion principle. So the concept, the protocol, how to compose multi-electron function as a something similar to product of single electron functions will be so-called Slater determinant. And if we will follow the thing, if we will, then it will give a good basis to respect Pauli exclusion and to include electron-electron interaction at a later stages. So the name of the method that we practiced yesterday is composed of two names, Hartree and Fock, right? HF, which is not hydrogen fluorine. The reason for two names is that first one was Hartree, and he did the same things that we are going to do in the next month, but he represented multi-electron function as product of one electron wave functions. He did literally separation of variables as people do in mathematical physics, in partial differential equations. And the Hartree method fails drastically. It's a nice theory, but it gives very much off numbers if one practices it. And the only achievement of Fock was to slightly modify a functional form of this multi-electron wave function in which we will seek for the solution. And he introduced the he brought Slater determinant into the method, took into account the antisymmetry of electrons, and then Hartree-Fock became, well, we know from the power of our today's achievement of modern science that Hartree-Fock is not perfect, but by the time it was designed, it was much better coinciding with experiment than anything else. So it was a big breakthrough. Right now, it may overestimate the gap like by 2 or 3 times, but any other methods were under or overestimating by orders of magnitude. So it was a really great breakthrough. Okay, so before we go to Slater determinant, we need to quickly overview the hydrogen atom and basis functions that we already started to do in the class verbally. So in case the electronic Hamiltonian has the kinetic energy of electrons, repulsion of electron to nuclei, and electron repulsion. In hydrogen atom, we do not have second and third electrons, so we have only first 2 terms, kinetic and energy and attraction to nuclei. And this is one of the problems that can be solved anytime. So the solution, well, it was one of the, it's one of the about 5 problems in quantum theory that can be found literally, and the solution is, so let me focus your attention on the black box in the middle of the slide. You see it? So it tells psi NLM equals R capital times Y capital, right? So this NL and M are quantum numbers that a lot of us see in freshman chemistry, principal, orbital, and magnetic. And the R capital and Y capital is factorization of this one electron wave function onto radial part and orbital part. And then for each of these factorized orbital and radial parts, there are expressions in special functions. Like there are exact mathematical expressions, which most likely we will never practice. We will just borrow them or use codes that already program them, but it's just pleasant for us to be aware that these functions are known, and hydrogen atom can be described even on the inhabited island with a single person without any computer, with sufficient math background. So this, I'll probably tell it on Tuesday, but this is a little feature which is aside from our main focus, but it is really helpful if you are thinking about plotting the orbitals. So the orbital part of wave function includes dependence on the M, magnetic quantum number, which is just accumulation of phase on a circle, and those functions are imaginary, which are very uncomfortable to plot. But if you do a trick and add together wave functions with opposite signs of the magnetic quantum number M, then this exponential stuff at the right, exponential with plus and minus factor, add together, and the dependence on angular motion converts into real part. So any orbitals we are drawing in freshman chemistry, they are not exact solution, but they are superpositions of the solutions for opposite values of magnetic quantum number. Because otherwise it will be hard for humans to draw imaginary things. So when you do this three-dimensional petals for d orbitals, x, y, d sub z square, they are already processed through this procedure. And here is the, yeah, what?
So is that why when we draw the orbitals, we can basically choose the phase interchangeably?
Pardon me? Just repeat.
Is that why when we draw the orbitals, the phases, we can basically choose the phase interchangeably?
Yes. Yes. But if one needs to describe magnetic field and Zeeman effect, when states with different magnetic quantum number change their energy due to magnetic field, then one needs to give up these pleasant functions and go back to complex shape. So, Kurt, do you recognize these figures? Have you seen them before?
Yes, I've seen those figures before.
Huh?
Yes, I've seen them before. I wouldn't know how to calculate them.
So, in which context did you see them before?
And I mean, we brushed on them in high school chemistry, and I just run across them.
Okay. Okay.
Since then.
Very good. Very good. So those are solutions of wave function in hydrogen atom, right? And these funny bubbles are centered around like a point in the center of or in a like point in the center of the circle for the first function, and then so one should imagine a positive ion in the center, and then electronic clouds wrap up around, and the red and green stay for positive and negative, but all of them are real here because when people draw these functions, one has already practiced removal of the complex thing. In some sense, one still draws these values of magnetic quantum number, because total number of independent solution doesn't change if you change the basis. And this figure just overviews our basis functions. We will never use literal hydrogen functions, because in Gaussian software the same shapes are represented by slightly more tractable functions, but the shapes will be the same, and one can later on we will be drawing molecular orbitals and recognize if they have some traces of atomic orbitals. So the first one, you see there are x's, right? It's like a little matrix, and the x's are labeled with L and M. L goes from 0, 1, 2, 3, and M goes from minus something to plus something, right?
Mm-hmm.
So when both L and M equal 0, it is the simplest function, which looks like just a cloud around the center. And here one shows isosurfaces rather than three-dimensional distributions. Otherwise, it will be too much complication. And if the L orbital quantum number is more than 1, then they start developing some fringes corresponding to circular motion. So this corresponds to Bohr model and standing waves corresponding to circular motion. And the higher this L quantum number, the larger the number of nodes and maxima in these things. And some of these orbitals look nicer, look like visually attractive. The magnetic quantum number tells it doesn't change total amount of rotation or angular momentum, but it corresponds to orientation of this rotation. Like if it is 0, it tells like magnetic quantum number tells if there is any rotation around z-axis. Like if magnetic quantum number is 0, you see its central column, then all shapes have nodal planes or nodal cones symmetric in x and y. There are like blob and the top and the bottom, and maybe some donut in between. But if magnetic quantum number increases, then it corresponds to rotation in x and y plane, and the larger this number, the more nodal planes appear in x and y plane. Okay, so it's just fundamental that we will later use, but it's not part of this course. And you have seen that I'm going to scroll back slightly. Scroll back. So here I'm focusing once again on this black box in the center, psi sub NLM, and it has factorized of R capital and Y capital. So there are two dependencies, one on angles and another on the distance from the center. Okay? So I'm going to jump a couple of slides forward. So this colorful figure corresponds to dependence on angles. It shows everything, but it gives more. It represents the Y function that depends on angles theta and phi. I probably should define them when I will be doing it on Tuesday. And another factor function is dependence on distance from center, R capital. And here are the R capital radial function for like several orbitals. So for the simplest solution, it is maximal near the center, and then it exponentially decays. For the next S orbital, S means there is no orbital motion, but there is a higher energy, there is a different principal quantum number. It has maximum at the center, then it drops, and then it raises again. And it's difference between 1s and 2s orbitals. And for p orbital, it has 0 at the center, and then it raises and drops. So by now we have overviewed quantitatively the solution for hydrogen atom, which will be a basis as one electron wave functions that like if you compose a molecule of many atoms, at each of the atoms there will be a set of such orbitals, populated or not populated with electrons, and then when they come together they will start interact, cross attraction of electrons to a foreign atom, repulsion of electrons, but the basis of these wave functions is a really good thing to start from. Make sense? Okay. So those wave functions will serve as building blocks for finding electronic wave functions with in molecules. So symmetry of electronic wave function. We briefly discussed it at the beginning. So I'm looking at the first. There are two equations, and I'm looking on the first one. So the here we consider capital phi multi-electron wave function that depends on two electrons. So maybe it was a helium atom, or maybe it was H2, a hydrogen molecule, just two electrons. And due to Pauli exclusion principle, due to the nature of electrons, there is a expectation that if one swaps the order of two electrons, then the sign of wave function changes. For many things, this tiny change is so the sign changes from plus to minus. You see here phi of R1 R2 equals minus phi of R2 R1, right? You see it in the first equation. On the left and right there is phi depending on two arguments, and we swap order of our arguments, which it means that we replace electrons in their either position in space or just their quantum numbers. So the nature of electrons, that sign of wave function changes. This is not always seen in the practical concepts. For example, if we are looking only for nice images and distribution of electrons in space, we are taking not wave function but wave function squared, p p capital of R1, R2, which is wave function absolute value square. And then change of sign doesn't affect anything. We will not see it on things on the spatial distributions. But this is the critical feature that needs to be taken into account to respect Pauli exclusion principle and later on to get right properties of molecules. So here is the little task that we will see the answer. We will see the solution of this task, but let me formulate it first. So we want to decompose multi-electron wave function onto single electron wave functions, like phi lowercase of R1 and phi lowercase of R2, which will be like hydrogen orbitals. But we want to compose a product, or maybe things similar to product, of this one electron wave functions in such way that upon swap of the order of electrons, the sign of the wave function will change. Okay. So here is the answer. Here is the solution for two electrons. So if instead of simple product, we will practice superposition of products. Superposition of products with different sign between them. Like if you will have for two electrons, it will be just two terms. So first term function, wave function with set of quantum states number 1 for electron number 1, and wave function with set of quantum numbers 2 for electron number 2, minus. So in second term, we keep the same order of electrons, like R1, R2, but we swap the order of wave functions. So first electron is in occupies wave function number 2, and second electron occupies wave function number 1. So the mathematical observation is that if one swaps the order, if one renames what was 1 becomes 2 and what was 2 becomes 1, the sign of this construction should change. Do you see it? If you do not see, if you are confused, let me know. I will try at least to improve it by Tuesday. So let's just get acquainted with it, and I'll try to be super convincing on Tuesday. But it is the shape of we will search for solution of multi-electron wave function in this functional shape. So instead of literal product of one electron wave functions, we will need to make product minus another product with different order of wave functions for two electrons. And if it will be like 3 and 4, it will be product of 4 or whatever electrons and 4 terms. So number of terms and number of elements in the product will grow. Okay? And the way to the last thing that we may want to discuss before completing and this thing and departing is so there is another little it's not a challenge, but it is a matter of practical convenience. So we can try to construct such products based on scientific intuition for each specific molecule, but it is not algorithmic. We need an algorithm how to compose antisymmetric wave function for in general case. Okay, and again, this challenge was already addressed by Slater. So please have a look on this last equation on this line, which is the same as on the previous slide. Phi of R1 R2 equals 1 over square root 2 f of R1 g of R2 minus g of R1 f of R2. So can we, like we already see in previous line that it has something to do with determinant. Can we establish correspondence with this expression and determinant of some 2 by 2 matrix? Like determinant of 2 by 2 matrix is product of diagonal elements minus product of the off diagonal elements, right? On Tuesday I will use facilities and will write things, but does it make sense what I'm mumbling about? Okay, so determinant is a main characteristic of a matrix, and if the matrix is as small as 2 by 2, like A matrix A, B, C, D, right? Then the definition of determinant is A times C minus B times D. Make sense? Now let's inspect this expression that we see in front of us. What if f of R1 is A, g of R2 is C, g of R1 is B, and f of R2 is D? Can we just imagine that it is a determinant of a matrix that is composed as FR1 GR1 in the first row and FR2 GR2 in the second row? Let's look. I should have written it on the next slide. So here the top line shows the definition of determinant, right? A, B, C, D, yes. Diagonals minus off diagonal. And if we will practice this definition for a matrix where first row has the same wave function, same quantum numbers, but different electrons. So first row has phi 1, but the arguments are R1, R2. And the second row has wave function with index 2, and again the arguments are R1, R2. Or if we are looking through the columns, then each element in column 1 has index R1, the argument, and each element in the second column has index R2, right? So now if you practice definition of determinant, then it will be two terms. First will be phi 1 R1, phi 2 R2, where index of electron coincides with index of quantum state. And the second one will be inverse order of the indices phi2 r1, phi1 r2. What was declared in order to have a good electronic wave function. So the suggestion of Slater was to compose a matrix of all independent wave functions of single electron along different rows and use electrons, like all electrons labeled independently as index of a column, and then find a determinant. And the statement is that if one practices such procedure for arbitrary number of electrons for any molecule, for any system with arbitrary number of orbitals and electrons, it will match Pauli exclusion principle. It will be good antisymmetric electrons. And it is critically important for us to follow this functional form when we will be designing or just learning how it was designed, learning the design of theories to find electronic structure. Okay. So I think we are done. It's thank you much for your dedication to the class and investing our unexpected vacation day for listening to it. Are there any questions that I need to answer now or prepare for Tuesday?
I've got nothing off the top of my head.
Okay. So was it too much for one meeting, or it's okay?
My major problem was just me forgetting terms that I learned 5-6 years ago.
Okay, but we will repeat them again and again and go over, so it will come up. Just major thing that it doesn't sound too challenging and too much, but remembering is not a problem. We'll go over it. Kurt, do you see any major challenges, or it looks reasonable and logic?
The math mostly makes sense. I'm gonna have to go and look up and research a few of these principles so I get a better understanding of it. But it's doable.
Okay.
It's not too much.
Okay. Very good. It was slides for some questions. Yeah. So I think it is reasonable time to complete the meeting. So imagine me standing with crossed arms, symbolizing end of the meeting. And I'll announce the email, the homework by email, which will be maybe doing the same thing as we did in class on Tuesday for slightly different potential, or maybe same potential with different initial condition, and maybe practicing to find total energy for really small molecules, same as we did in the lab.
Okay. Can we use Excel spreadsheet for it, or do you want it all hand drawn out?
I don't care about shape. If you can do Excel, great. Even if you do it instead of calculator, if you write a little script that will print out the steps, it's even better.
Okay.
I just do not want to overwhelm anyone with too much things. But for some people, it's easier to write a script and run it rather than hand write and use calculator.
All right.
Okay, yeah. Thanks again, and I'm going to complete and log out of the meeting.
Okay. See you on Tuesday.
See you on Tuesday. Have a nice weekend.
Bye.
Okay, bye-bye now.